Hey everybody, I'm going to walk you through one of the most common measurements we make in kind of water relations of plants, and that is measuring the water potential of water in a plant. So in your reading, you should have read a little bit about what water potential is, but just to review, water potential is a measurement of the potential energy of water. And so the standard or the reference we use for potential energy of water is just pure water that's at a standard temperature and pressure. So, for example, the water in this glass has a water potential really close to zero. And so if we were to do something to increase or decrease the potential energy of this water, that would change its value. So if we were to do something to increase its potential energy, then we would have positive values of water potential. So for example, if I were to raise this, it's got more potential energy because it's higher off the ground, and that gravitational pull increases that potential energy. Alternatively, if I were to add some salt or some sugars to this water, they would interact with the molecules, decreasing their movement and decreasing the potential energy. Likewise, if I put some strain on the hydrogen bonds of those water molecules, it would also reduce the potential energy of that water. If we reduce the potential energy, then we're talking about negative numbers, because relative to this pure water, it's got less potential energy, and those are negative values. So in plants, the water inside the plant in some places is pretty pure, but within all of the living cells, there's solutes in there that are going to reduce that potential energy. Likewise, there's strain on those hydrogen bonds from the evaporation of water from the leaves, which also decreases the potential energy of that water. So in plants, we're most of the time talking about negative values. There's some situations that can get positive, but for the most part, we're talking about negative values. And the kind of relative value of the water potential gives us some indication of water status in a plant. So the more negative it is, the less potential energy there is in that water, and generally that means the plant is kind of more water stressed. But certainly there's some plants that are adapted to work at low water potentials and some that are adapted to work at high water potentials. So it's kind of all relative to the starting point of each individual species. In a plant, in the reading, you've read about the soil plant atmosphere continuum, or the SPAC. And so the water column is kind of this continuous column of water from the soil through the plant and then into the atmosphere. And so the atmosphere is generally, at least relative to the plant tissue in the soil, is pretty dry. So the water potential of water vapor in the air is really, really negative. We're talking minus 100 megapascals, or in that ballpark. So that really dry air pulls water, or helps convert liquid water in the leaf to vapor water that then leaves through the stomate. And so as that water converts from liquid to vapor, it creates a pull on that water column, or it reduces the water potential where that water is evaporating. And so we have relatively low or negative values in the leaf. And then that low water potential is causing water to move from places of relatively high water potential to low water potential. So the soil is relatively high water potential compared to the leaf and to the atmosphere. And so that's why water is moving up through the plant. And in some ways, you could just think of the plant as a giant resistor between the water in the soil and the water in the atmosphere, and it just kind of like is this conduit that acts as a resistor between those two pools of water. So we can take advantage of this kind of water column in the plant to measure water potential. So when this plant is actively transpiring, we know that the potential energy of water in this plant is going to be fairly negative, but of course there's going to be some gradient from soil to leaf. However, if we were to cut the leaf, for example, the water at that cut surface is going to be exposed to atmospheric pressure and is going to have the potential energy something about like this glass of water. So it's going to be really close to zero as soon as we cut it. All right. So what happens if we were to cut this leaf, for example, here? the water here would be at atmospheric pressure, or close to zero, and let's say the water here is going to be at some negative value. So as soon as we cut it, the water is going to move up inside this leaf because of this negative water potential here. So it's going to kind of pull the edge of the water column up away from the cut surface. And the same thing would happen on this side of the leaf. Because the soil is more negative than atmospheric pressure, or than zero, the water that's right here would get pulled up into the leaf in that direction. And so what we're going to do is kind of take advantage of the fact that that water gets pulled up in the leaf to try to estimate the water potential of the water column right before we cut the leaf, by applying positive pressure to the leaf to force the water column back to the cut surface. And the positive pressure it takes to push the water back to the cut surface is the same, kind of the opposite sign as the water potential that it was under before we cut it. So the amount of negative pressure there was to pull the water up is offset by the positive pressure it takes to push that water back. So we're going to put positive pressure on it, and whatever the value we get for that positive pressure that it takes to push the water column to the cut surface is the negative pressure or tension that the water column was under before we cut the leaf. So I'm going to walk you through the measurement real quick, and then I'll try to get a zoom in so you can actually see this working. So this is a pressure chamber, and it is like one of the most basic scientific instruments we use. Underneath here is really just a series of stainless steel tubes routing gas from one place to another, and then hooked to a regulator that tells us the amount of pressure. What we have here is a chamber, and I'll show you the inside of this chamber in just a minute, and then a cap that goes on this chamber. And you can hopefully see that there's a little bit of a hole in the lid of this chamber. And so what we're going to do, we're going to start with a sunflower. So I'm going to, in a few minutes, I'm going to cut this leaf at the petiole. And again, because there's negative water potential in the leaf, it should pull the water up inside that petiole. Then I can take this petiole and put it up through this hole in the chamber. And then the leaf part, the lamina, would be on the bottom part. I'll put this in the chamber and seal this lid. And then I can open a tank of compressed nitrogen, which is under the table here. And that compressed nitrogen will slowly fill up the chamber, building up positive pressure. And I'm going to watch the cut surface of the petiole until I see the water come up to that cut surface. And then I'm going to stop the flow of nitrogen into the chamber and then read what the positive pressure is in that chamber. And again, that positive pressure represents, the pressure it took to balance the tension that water column was under. So that's the basic premise of it. This instrument was kind of designed and developed in Oregon in the 1950s. And this company that this instrument came from is the same company that helped develop the instrument, and so they've been around and producing these instruments ever since. And to be honest, the design has changed very little. So it's a very good, solid, robust design that's stood the test of time, if you will. Okay, I've got a closer view here of the instrument and the setup, and so I'm going to walk you through how we'd make a measurement. And then I'll do another one where I get closer in and you can actually see the cut surface of the leaf. So first thing I'm going to do is cut this leaf on the petiole, and I'm going to leave a decent amount of the petiole because the petiole is going to have to pass up through the bottom of this chamber and then stick out the top a little bit so I can actually see it. I'm going to use just a razor blade and a piece of rubber to cut it on. You can also use scissors to cut this, and that works just fine. The razor blade just gives it a really nice clean cut, and sometimes it's easier to see that water reach the cut surface. So I'll go ahead and do this real quick. So I'll just put this up through the bottom here, and the lamina again is going to stay on the bottom. And maybe you can see it sticking up, and then I turn this. As I turn this this piece here, it tightens the gasket so we get a nice seal around that petiole, and you get it really tight. You're not going to damage the xylem inside, which is where the water's moving through, so you can really crank down on it. Now I'm going to put this in the chamber and got to push down and turn it so it locks. And we're dealing with thousands of psi of pressure, so it's potentially kind of dangerous apparatus, I guess. And so we need to be careful in ensuring that everything is locked down and sealed before we actually start the pressure. So what I'm going to do here is we just have this lever between chamber, off, and exhaust. So when I click it to chamber, that means the compressed gas that's coming through this tube will actually be channeled into the chamber. If I turn it off, it just stops the gas, and if I go to exhaust it, it exhausts it and releases that pressure. So I'm going to do it to chamber, and then this little needle valve is closed right now, and if I open it, the pressure will start increasing. So I don't know if you can see the needle increasing over here. I'll zoom in on this in a little bit. So I'm going to exhaust it. I'm going to go back to chamber. Now what I'm going to do is I'm going to look at this cut surface while I let pressure into the chamber, and as soon as I see water come on this cut surface, I'll stop the flow of air to the chamber. And I'm going to use a hand lens so I can see this really well. Okay, so these are really well hydrated, so this was a pretty quick measurement. I'll just, I don't have fancy gear, so let me zoom in here a little bit on the, hold on, you gotta be patient because I don't know what I'm doing. All right, there you can see the regulator. The numbers on the inside are in the units of bar. On the outside is PSI. For water potential in plants, we're generally using megapascals. And so the way to convert from bar to megapascal is just to take the bar value and divide by 10. So you can see that the needle is pointing at about 5 bar. This would be 0.5 megapascal. So what that means is it took 0.5 megapascals of positive pressure to force the water back up to the cut surface. So we are then assuming that the tension on the water column before we cut it was -5 megapascal. And so that's how we're estimating the water potential inside the plant. All right, so I'm going to stop it here. Okay, what you're looking at now is the cut surface of a twig from a Siberian elm tree that's growing in my backyard. So I've got it in the pressure chamber right now, and currently the chamber is being filled with positive pressure just from N2 gas, and so the positive pressure is building up, slowly pushing that water column up to the cut surface. And so what we're looking for is the moment where we first see bubbles showing up on this cut surface of the twig. And if we were making this measurement for real, as soon as we would see those bubbles, we would stop that flow of air into the chamber, look at the regulator, and take a reading from that regulator to know how much positive pressure it took to force that water up to the cut surface. And again, then that represents the negative pressure that water column was under when we cut it. Okay, right there on the left side kind of, and now you see it spreading. And so right when we first saw that bubble, that's when you would want to take a reading. And here in a second, I turn off the flow of gas in the pressure chamber, and then that water will slowly resorb back into the stem. And that's our measurement of water potential.